You've used ChatGPT. You type a question, and a perfect answer just appears. It feels like magic. But what if I told you the entire secret to that magic is this? Now, don't worry, I know this looks like a wall of code. This is the complete GPT-2. And right here, this first part, this is the causal self-attention block. It's the absolute heart of GPT. We're going to break this down completely. And the next piece is the MLP and the transformer block. This is what processes the information from the attention mechanism. It's the thinking part of the network. And finally, you put it all together into the full GPT-2 model class. It's just the embeddings, those transformer blocks we saw, and an output layer. That's it. These roughly 100 lines of Python contain all the core architectural ideas behind multi-billion-dollar models like GPT. There is no hidden code, no secret sauce. My promise to you is simple. Give me 100 minutes and I will make the transformer click for you forever. We are going to walk through this file line by line. You will understand not just what each line does, but why it's there. That is the key. The magic will dissolve into understandable, elegant engineering. This diagram is our roadmap. Look at it here. We're going to see this a few times. We will start at the very beginning with embeddings, which turn words into vectors. You can see them highlighted in green at the bottom. Then we'll build the core engine, the transformer block. You see it here in orange. This is where the real work happens. Finally, we'll build the output layer that makes the prediction. That's the purple block right at the top. The most important component is causal self-attention. It's all governed by this one formula. Attention of QKV equals softmax of QK transpose over the square root of D sub K plus a mask M all times V. I know this looks intimidating now. I totally get it. Trust me. By the end of this video, it will be second nature. Every project starts with a blueprint. For us, that's the GPT Config. It's a simple data class holding all our parameters. We have vocab underscore size, block underscore size, n underscore layer, n underscore head, n underscore EMBD, and dropout. These are the knobs you turn to make the model bigger or smaller. Let's look at this table together. We're going to walk through this step by step. First up, we have vocab size. This controls the vocabulary size, or how many unique words the model knows. For the real GPT-2 Small, this was 50,257. Next, block size. This is the context window. It's how far back the model can see at once. GPT-2 could see 1,024 tokens into the past. Then, N layer. This is the model depth. It's how many of those transformer blocks are stacked on top of each other. More layers means a more powerful model. The small version had 12. After that comes N head. This is the model limb, commute. It controls how many parallel conversations the attention mechanism can have at once. We'll dive deep into this. GPT-2 also used 12 for this. And finally, N underscore EMBD, the embedding dimension. This is the size or richness of the vectors that represent each token. GPT-2 used a size of 768. So by just changing these numbers, the exact same 100 lines of code can create a tiny toy model or the full-scale GPT-2. It's incredibly flexible. With our blueprint in hand, we're ready to lay the first brick. Next, we will build the embedding layers that turn symbol numbers into the rich vectors our model needs. Let's get our hands dirty. Our journey starts with the very first functional layer of the model. Let's look at our code blueprint and find exactly what we're building. Look here on the screen. We have our class GPT-2, which inherits from nn.module. Inside the init method, we are building this line right now, the one that says self.wte equals nn.embedding with config.vocab_size and config.n_embd. This is the word token embedding. The next line, WPE, well, that's the next chapter. So why do we need this? What problem are we actually solving? Well, here's the problem. Raw token IDS. The input to our model is a sequence of numbers, like an array of 5, 21, 108. But these are just meaningless IDs from a vocabulary list. A neural net can't do math on them. It just doesn't work that way. Think about it. The number 21 isn't 4.2 times more word than the number 5. That's absurd. The distance between them is completely meaningless. So how do we give these numbers meaning? Our goal is to map each token ID to a vector. A vector is just a list of numbers representing a coordinate in space. And here's the key idea. The location of these coordinates should actually mean something. Let me give you an analogy. Let's think about representing colors. A bad way, just like our token IDs, would be to assign them arbitrary numbers. Maybe a dictionary, where red is 1, orange is 2, and blue is 8. A computer sees 8 and 1, but has no idea that orange is supposed to be between red and blue. The numbers are completely arbitrary. Now, a good way would be to use vectors. We can represent colors in a coordinate system. Let's say the x-axis is redness and the y-axis is blueness. In this system, red could be the vector 0.9, 0.1. Orange could be 0.8, 0.2. See? It's super close to red. And blue could be 0.1, 0.9, which is way far away from red. Now the distance between points is meaningful. We're going to do the exact same thing for words, but in a space with 768 dimensions. The mechanism for this is the n.embedding layer in PyTorch. It's nothing more than a giant lookup table. You can think of it as a learnable coordinate book. Let's build one and look inside. We'll import torch and torch.nn. We'll set up a tiny config for our example. Let's say vocab_size is 10 and n_md is 3. That's the number of dimensions in our semantic space. The layer itself, which we'll call token_embedding_table, is just nn.embedding with vocab_size and n_md. The book itself, the actual coordinates, are in the .weight attribute. Each row is a word's coordinate. Let's print the shape of our coordinate book, and then let's print the actual content. And here's the output. Check it out. The shape of our coordinate book is torch.size with 10 rows and 3 columns. Makes sense. And the content of the book is a tensor filled with initially random coordinates. You can see the first row is the coordinate for token 0. The second row is the coordinate for token 1, and so on, all the way down to token 9. And notice it says requires grad equals true. This is the core. It's really just a matrix of shape, vocab_size by n_mbd. That's all it is. And did you see that requires grad equals true part? That's the magic. It means during training, the model will learn the best possible coordinates for each word to help it make better predictions. The model itself will figure out what redness and blueness mean for words. We've successfully transformed our data. Our input of meaningless integers like 2, 5, 1 becomes an output of rich 3D embedding vectors. Each token now has a rich 3D semantic representation. So what have we gained? We now have a representation where words with similar meanings will end up close to each other in this high-dimensional space. This is what enables the famous vector math analogy you've probably heard of. The vector for king minus the vector for man plus the vector for woman is approximately equal to the vector for queen. It's incredible. But this representation has one massive flaw. It is stretted and context-free. The vector for the word bank is identical in these two sentences. Number 1, I sat on the riverbank. Number 2, I withdrew money from the bank. The embedding layer has no idea which bank we're talking about. It just gives back the same vector every time. This is the central problem the transformer is designed to solve. How can a token's vector be dynamically adjusted based on its context? To even begin to answer that, we first need to give the model a sense of order. Let's locate our next component in the code blueprint. We've built the word token embedding, the WTE. Now, we are building this line right now, self.wpe, which is another in.embedding layer. This is for the word positional embedding. So how do we do it? The solution used in GPT is wonderfully simple and elegant. Think about this. Just as we learned a unique vector for each word, we will now learn a unique vector for each position. It's that simple. Each position gets its own unique vector. So there's a vector that literally means I am at position 1, another for I am at position 2, and so on, all the way up to our maximum sequence length, the block size. And how do we implement this? It's another in embedding layer. It's a lookup table, but this time for positions, not for words. Now, you're probably asking the key question. Why does adding the position vector to the word vector work? Won't that just scramble all the information we so carefully created? Here's the key insight. It works for a few reasons. First, they exist in the same space. Both the word vectors and position vectors live in that same 768-dimensional space. Second, adding them creates a unique point in that space. The model learns to create positional vectors such that adding them to a word vector creates a new, distinct representation. So the word the at position 5 is now a completely different point from the word the at position 20. The network learns to understand this distinction. Let's see this in code. It's always the best way to make it click. Okay, let's walk through this together, line by line. First, our tiny config. B, T, and C are 2, 5, and 3. That's our batch, time or sequence length, and channels or embedding dimension. Our vocab size is 10, and our block size, our model's maximum sequence length, is 8. Now for the layers. First, we have the same token embedding table from the last section, nothing new there. And now the new one, the position embedding table. Notice its vocabulary is the block size. It has 8 possible positions it can represent. Okay, next up, the input data. We'll create a random tensor of token IDs called IDX with a shape of 2 by 5. All right, step 1. Get the token embeddings, just as before. We pass our IDX into the token embedding table. The result, talk worship, has a shape of 2 by 5 by 3. Now for step 2, the new part, getting the positional embeddings. We only need the positions for our current sequence length, t, which is 5. So we use torch.arrange from 0 to t, which gives us a tensor of 0, 1, 2, 3, 4. We then look these position IDs up in our new position embedding table. The result, pos embed, has a shape of 5 by 3. And for step 3, we combine them. It's just simple addition. X equals talkbed plus pos embeds. Finally, let's print the shapes and see what happened. And here's the output. The shape of our token embeddings is torch.size of 253. The shape of our positional embeddings is 53. And the shape of the final combined embeddings is 253. Now, look at those shapes again. How can you add a 2 by 5 by 3 tensor to a 5 by 3 tensor? The answer is PyTorch uses broadcasting. PyTorch is smart. It automatically takes that 5 by 3 position tensor and adds it to each of the 2 sequences in our batch. It just works. It's incredibly efficient. This also answers another key question. What if our sequence length is less than the block size? This is the common case. Our block size is 8, but our current sequence length, t, is only 5. The solution is that smart line of code, torch arrange from 0 to t. It only generates the positions for the actual sequence length we're processing right now. The result? Perfect automatic handling. It just works. We have now prepared the input for the main event. Our tensor X contains vectors that are now aware of both a token's identity and its absolute position in the sequence. This is the input that will flow into the stack of transformer blocks. It's time to build the heart of the machine. We've laid the foundation. Every word has a vector. Every position has a vector. But we still have the riverbank versus moneybank problem. Our model has no way to adjust a word's meaning based on its context. This is the heart of the transformer. To make this crystal clear, let's forget code for a moment and focus on one single ambiguous word. Crane. First sentence. The crane ate a fish. Here, crane is obviously a bird. Second sentence. The crane lifted the steel. Here, crane is a machine. Right now, the starting vector for crane is identical in both sentences. We need a mechanism to update this vector based on its neighbors. That mechanism is called self-attention, and this is its formula. Attention of QKV equals softmax of QK transpose over the square root of D sub k all times V. I know it looks complex, but by the end of this section, you'll understand it intuitively. The entire process happens in 3 steps. 1. Scoring. 2. Normalizing. And 3. Aggregating. But first, what are Q, K, and V? They are 3 distinct vectors for every single word, created by projecting the input vector, X. The query, or Q, is the word's search query. It's what it's looking for. The key, or K, is the word's label, or keyword. It's what it is. And the value, or V, is the word's payload, the information it offers. Now you might be asking a brilliant question. Why do we need a separate value vector? Isn't our input vector X already the information? The V vector is a transformed version of X, packaged for others to consume. Look at this table. The input vector X is like your entire knowledge and resume. It's the raw, complete information. But the value vector V, that's your prepared elevator pitch. It's packaged, consumable information that's ready to be aggregated. It's made from a learned transformation of X. The model learns the best elevator pitch for each word. Okay, analogy over. Let's see the numbers. We'll use a dead simple 2D space. Dimension 1 represents, is it an animal? And dimension 2 represents, is it a machine? Here are the vectors for our words. Check out this table. Notice the crane vectors are all ambiguous, like 0.7, 0.7. But 8 and fish are high on the animal dimension, and lifted and steel are high on the machine dimension. All right, sentence 1. The crane ate a fish. We're going to walk through this step by step. First up, scoring. The crane's query, which is 0.7, 0.7, is going to probe every other word's key. Let's do the math. The score for crane looking at itself is 0.7, 0.7, dotted with 0.7, 0.7, which equals 0.98. That's a high self-affinity. Now the score for crane looking at 8 is 0.7, 0.7, dotted with 0.9, 0.1. That equals 0.70, a high match. And crane looking at fish, it's 0.7, 0.7, dotted with 0.8, 0.2, which also equals 0.70, another high match. Step 2, normalizing. We take those raw scores, 0.98, 0.70, 0.70, and we run them through softmax to convert them into percentages. The result? Our attention weights are 0.4, 0.3, 0.3. This is the aha moment. Crane has decided it will listen 40% to its original self, 30% to 8, and 30% to fish. Okay, step 3, aggregating. We take those weights and multiply them by the value vectors. So the new vector for crane is 0.4 times the value of crane, which is 0.5, 0.5, plus 0.3 times the value of 8, 0.9, 0.1, plus 0.3 times the value of fish, 0.8, 0.2. That gives us 0.2, 0.2, plus 0.27, 0.03, plus 0.24, 0.06. The new vector for crane is now 0.71, 0.29. It is heavily skewed towards dimension 1, animal. The ambiguity is resolved. Now let's do sentence 2. The crane lifted the steel. The process is the same, so let's move a bit faster. First, scoring. The crane's query is the exact same as before. It probes the new words. And look at this. The scores are identicable. 0.98, 0.70, 0.70. So for step 2, normalizing, the attention weights are the same. 0.4, 0.3, 0.3. Here's the kicker. They're applied to different context words. So for our final step, aggregating, we take our weights and apply them to the new value vectors. It's 0.4 times the crane value, plus 0.3 times the lifted value, plus 0.3 times the steel value. This becomes 0.2, 0.2, plus 0.03, 0.27, plus 0.06, 0.24. And there it is. The new vector is 0.29, 0.71. Now heavily skewed towards dimension 2. Machine. The exact same initial crane vector has been transformed into 2 completely different context-aware vectors. This is the power of self-attention. It's a communication mechanism that allows every word to dynamically pull in information from its context to refine its own meaning. We've built the intuition. We saw how the word crane could resolve its ambiguity by listening to its neighbors. Now it's time to translate that exact process into the language of linear algebra. Fast, efficient matrix operations. Our map for this section is the formula itself. Look at this on your screen. We are going to build this step by step. Attention of Q, K, and V equals softmax of Q times K transpose divided by the square root of D sub K, all of that, times V. I know, it might look a little intimidating, but we are going to build it piece by piece, and it'll make perfect sense. First, we will build this with raw tensors to see every single number. Then, we will encapsulate that logic into a clean, reusable PyTorch node. Part 1. The raw tensor walkthrough. Let's use a simple 4-word sentence, so t equals 4. We'll use a tiny embedding dimension, c equals 2, and we'll process one sentence at a time, so b equals 1. Okay, let's import torch, torch.nn, and a few other things we'll need. We set b, t, c to 1, 4, and 2. Now here's a pretend input tensor from our embedding layers for the sentence, a crane ate fish. We'll call it x. It's just a torch.tensor with the values you see here on the screen. Step 1. Projecting x into q, k, and v. To get our query, key, and value vectors, we use learnable linear transformations. These are just standard PyTorch nn.linear layers, so we'll define a q_proj, a k_proj, and a v_proj. Now, just to make this tutorial reproducible, we'll manually set the weights using torch.manualseed42. This way, you can get the exact same numbers I do. And now, we perform the projections. Q equals q_proj of x, k equals k_proj of x, and v equals v_proj of x. Simple as that. Let's track our tensor shapes. This is the most important habit to build. Seriously. Look at this table. Our variable x has the shape 1, 4, 2. That's our batch of raw input vectors. After the projection, q, k, and v all have the exact same shape, 1, 4, 2. They represent the query, the key, and the value vector for each of our 4 tokens. Okay, step 2. Calculate attention scores. This is the core of the communication. We compute the dot product of every token's query with every other token's key. So, q has a shape of 1, 4, 2. To multiply it with k, we need to transpose k's last 2 dimensions. So, k.transpose of -2, -1 gives us a new shape of 1, 2, 4. The resulting shape? A 1x4x4 matrix. Here's the code. Scores equals q @ k.transpose -2, -1. And here are the raw scores, the attention matrix. It's a tensor of size 1, 4, 4. Let's look at this closely. The first row shows the scores for A looking at every other word. The second row is for crane looking at every other word. And look at that second row. It has the highest score, 1.3888, with itself. This makes perfect sense. A word is usually most related to itself. Step 3 and 4, scale and softmax. We scale for numerical stability. Then we use softmax to turn each row into weights that sum to 1. So first, we get d sub k, which is just the size of the last dimension of k. Then, scaled scores equals scores divided by math.square root of d sub k. Finally, attention weights equals f.softmax of the scaled scores along the last dimension. Step 5. Aggregate the values. This is it. Now, we use our calculated weights to create a weighted average of the value vectors. Our attention_weights tensor has a shape of 1, 4, 4. Our v tensor has a shape of 1, 4, 2. The resulting shape is 1, 4, 2, exactly what we started with. The code is simple. Output equals attention_weights @ v. And here's our final output. a tensor of size 1, 4, 2, containing our new context-aware vectors. Here is a summary of the entire process. Look at this table. Step 1, we create Q, K, and V. Step 2, we multiply Q and K transpose to get raw scores. Step 3, we scale by the square root of D sub K. Step 4, we apply softmax to get attention probabilities. And step 5, we multiply those probabilities by V to get our final context-aware output vectors. Success! We've transformed our input X into an output of the exact same shape, where each token's vector is now context-aware. Part 2. Encapsulating the logic in an NN.module. The raw tensor walkthrough is fantastic for understanding, but in practice, we package this logic into a reusable class. This makes our code clean, organized, and easy to stack. Here is the final reusable module. By the end of this section, every single line will be crystal clear. We define a class, single head self-attention, that inherits from NN.module. Inside the init, we define one linear layer. And in the forward pass, we do all 5 steps. Let's look at the __init___ method, the fused linear layer. Instead of 3 separate linear layers, we use one larger, much faster one. The manual walkthrough on the left is conceptually clear, but the fused layer on the right is computationally efficient. We define a single layer, C_ATTR, that goes from our embedding dimension to 3 times the embedding dimension. Now, the forward method. Projection and splitting. First, we get QKV equals self.c_ATTN of x. This produces a big tensor of shape BT 3 times C. Then we do something clever. QKV equals QKV.split with C along dimension 2. This carves that big tensor up into 3 chunks of size C. This gives us back our separate Q, K, and V tensors, each with the shape BTC. The rest of the code is a direct one-to-one implementation of the formula we just walked through. It's identical. It works perfectly. We have successfully implemented the core of self-attention and formalized it in a clean, professional module. However, our model has a flaw, a big one. For language generation, tokens can see into the future. In our current setup, the word A can see crane, 8, and fish. When we're generating text one word at a time, that's cheating. Let's think about what we're trying to do. We want to build an autoregressive model. It's a fancy term for a model that generates text one token at a time. When predicting the next word for a crane 8, its decision must be based only on tokens it has already seen. A crane 8. It cannot be allowed to see the actual answer, fish. But look at the attention matrix we calculated. Check this out. The first row for A is attending to all 4 tokens. That's cheating. The second row for crane also attends to all 4 tokens. This is a huge problem. A token at position T must only be allowed to communicate with tokens from the past, from positions 0 up to T. It cannot see the future. The solution is as elegant as it is effective. The causal mask. We will modify the attention scores before softmax. We mask out future positions by setting their scores to -infinity. Now, why -infinity? This is the key technical trick. The softmax function involves an exponential, You see the formula here. It's e to the power of x sub I divided by the sum of all the e to the power of x's. So what is the exponential of negative infinity? E to the power of negative infinity is approximately 0. By using negative infinity, we force the attention weights for any future tokens to become 0. It's brilliant. Let's see this in action. This is the visual aha moment. We'll start with the setup, raw scores. We pick up with our scaled scores matrix from earlier. You remember this one, right? The shape is 1, 4, 4. I'll just put the tensor up on the screen here. Step 1. Create the mask. A lower triangular matrix is perfect for this. We can get one with torch.trill. 1s are positions we keep, and 0s are the future positions we're going to block. So we set t equals 4, and our mask is torch.trill of torch.1s of t, t. And here's the mask it creates. Look at this. Row 0 for A can only see column 0, A. Makes sense. Row 1 for crane can see columns 0 and 1, so A and itself. The zeros are what block those future connections. Step 2. Apply the mask. We replace all values in scaled scores with negative infinity wherever our mask is equal to 0. The code is masked scores equals scaled scores dot masked fill, where mask equals 0 with float of negative infinity. And here are the scores after masking. Look at that beautiful upper right triangle. It's all negative infinity. Perfect. All future positions have been obliterated. Step 3. Rerun softmax. Now let's apply softmax to these masked scores and watch the magic happen. Attention major equals f.softmax of masked scores along the last dimension. And here are our final causal attention weights. This is it. The upper right triangle is now all zeros. A only attends to itself 100%. Crane attends to A and itself. 8 attends to A, crane, and 8, and so on. We have fixed the time-traveling bug. Let's look at this table. For the unmasked attention, could crane attend to fish? Yes. Could 8 attend to fish? Yes. But now with causal attention, the answer to both is no, 0%. Problem solved. Part 2. Encapsulating in the inin.dot module. Let's look at the init method and a cool function called register buffer. We need to store our mask as part of the module, but it's not a trainable parameter. For this, we use register buffer. So inside our class causal self-attention, we call self.registerBuffer. We'll name it bias, and we give it our torch.trill mask. So, quick quiz, what's a buffer? A buffer is a tensor that is part of the model state. It gets saved with the model's state dict. It moves to the GPU with .toDevice, but it is not a model parameter, so it is not updated by the optimizer. It's perfect for our fixed causal mask. Now for the forward method. The forward pass is updated with one crucial line right before the softmax. After we calculate our scaled scores, we add the new line. Scaled scores equals scaled scores.maskedFill, using our stored buffer, self.bias. We slice it to match the current sequence length t, and again, wherever it's 0, we fill with negative infinity. Then we just run softmax like before. We have now built a fully functional, causal, single-headed attention mechanism. It can learn context, but it can no longer cheat. But it's still just a single attention mechanism. It's like one person in a meeting trying to track everything at once. Grammar, meaning, long-range context, all at the same time. That's a lot of pressure. To make it truly powerful, we need to allow it to have many conversations at the same time. So, what's the solution? You hire a team of specialists! This is the core idea of multi-head attention. Instead of one overworked mechanism, we have several working in parallel. Head 1 might become a specialist in syntax, verb-object relationships. Head 2 might specialize in semantics, like related meanings. Head 3 might track pronoun references. And so on. The entire process follows a simple narrative. Look at this diagram. It's just split, then attend, then merge. That's it. Part 1. The raw tensor walkthrough. Let's use the actual dimensions from the GPT-2 small model to make this real. Our embedding dimension, C, is 768. The number of heads, n_head, is 12. And that means the dimension per head, head_dim, is C divided by n_head, which is 64. Okay, let's walk through this together, step by step. Step 1. Splitting C into n_head and head_dim. We'll start with a dummy Q tensor with a realistic shape. Let's say Q equals torch.random with B, T, C. So a batch of 1, a sequence length of 4, and our embedding dimension of 768. First, let's look at its starting shape. We print the original Q shape and we get torch.size of 1, 4, 7, 6, 8. Makes sense. Now for step 1.2, the dot view operation. Here's where we carve up that last dimension. The code is q_reshaped equals q.view with b, t, n_head, and head_dim. And look at the new shape. After dot view, it's torch.size of 1, 4, 12, 64. We've successfully created our head dimension. But we're not done. Step 1.3, the dot transpose operation. This is so important. We need to bring the number of heads dimension to the front. This isolates the heads so PyTorch can process them all in parallel. The code is q_final equals q_reshaped.transpose, switching dimensions 1 and 2. So the final reshaped Q shape is now 1, 12, 4, 64. The key insight is in that final transpose. We move the n_head dimension to the front so PyTorch's broadcasting will treat it like a new batch dimension. All our attention math will now happen 12 times at once, independently. Step 2. Run attention in parallel. We do the exact same reshaping for K and V. So K_final and V_final both get reshaped and transposed into that same 112,464 shape. Now for the attention calculation, which is happening 12 times at once. We multiply Q_final by K_final transposed. That's a BNHTHD matrix multiplied by a BNHHDT, which gives us a BNHTT. Then we scale it. We apply softmax. And finally, we multiply the attention weights by V_final. So a BNHTT matrix times a BNHTHD gives us our final output per head. And if we print the shape of the output from each head, we see torch.size of 112,464. Perfect! Each of our 12 specialists has done its job. Step 3. Merging the heads. Time to bring the team back together. First, we transpose and reshape to merge the heads. The code is merged_output equals output_per_head.transpose 1, 2, followed by .contiguous and .view BTC. And if we check the shape of the merged output, it's back to 14768. Then, we pass it through the final projection layer. C_proj equals nn.linearcc. And final_output equals C_proj of our merged output. The shape of the final output is 14768. Here's the entire journey in one table. First, we split the heads, going from BTC to BNHTHD to prepare for parallel computation. Second, we run attention, where each head computes context independently, keeping the same shape. Third, we merge the heads, going back from BNHTHD to BTC to combine all the insights. And finally, a final projection mixes the information, keeping the BTC shape. And we're back. Each token's vector now contains the combined context-aware information from all 12 attention heads. Part 2. Encapsulating in the NN dot module. Let's look at the init method first. We add the final projection layer and an assert to make sure the dimensions are compatible. Inside our causal self-attention class, we have self.cViewpoints equals nn.linear from config.nprime to config.ncalsed. Simple as that. Now for the forward method. Part 1 is the split. We get our B, T, and C from the input size. We get Q, K, and V, and then we do the exact same view and transpose operations we just walked through manually. Q equals Q.viewBT, self.nhead headdarms, and then .transpose 1, 2. We do the same for K and V. Next, the forward method, part 2, attend. This should look very familiar. We run causal self-attention on each head in parallel. We calculate ATT with the matrix multiplication and scaling. We apply our causal mask using masked fill. We run softmax, and we get our output Y by multiplying ATT and V. And finally, the forward method, part 3, merge. We take our output Y, we transpose it, make it contiguous, and view it back into the BTC shape. Then we pass it through our final projection layer, Y equals self.cproj of Y, and we return Y. Every single line in this module should now be crystal clear. We have successfully built the communication layer of the transformer. That was the causal self-attention module. It's the big group meeting where all the tokens get together and share information. But after a big meeting, what do? You go back to your desk to sit and think. You process all that new information on your own. This is the exact role of our next component, the MLP, the thinking layer. And after the sheer complexity of attention, this is refreshingly simple. Check out the code we're about to build from gpt2_min.py. We have a class MLP that inherits from nn.module. Inside the init, we have a fully connected layer called FC, a projection layer called proj, and a dropout layer. And the forward pass is just a few lines. That's it. So let's break down the roles. The attention layer allows tokens to interact with each other. That's the communication part. The MLP layer, however, processes information for each token independently. This is the computation or thinking part. This structure, communication followed by individual computation repeated over and over, is what gives the transformer its power. The standard architecture for the MLP in a transformer follows a pattern I call expand and contract. Let's walk through it. 1. Expansion using the FC layer. We project from our embedding dimension, n embed dimension, up to 4 times that size. 2. Nonlinearity. We apply an activation function, in this case, GELU. 3. Contraction using the proj layer. We project that huge vector back down to the original n_embed d size. And 4. Dropout for regularization. Okay, before we build the whole MLP, let's demystify its core component, nn.linear. It's honestly just simple math. The output is just the input times the weight matrix transposed plus a bias. No more magic. Let's prove it. Our problem. We want to demystify nn.linear by projecting a vector of size 2 up to a vector of size 4. We'll import torch and torch.nn. We set our input channels Cin to 2 and our output channels Cout to 4. Then we create our linear layer. Now, this layer has 2 learnable parameters. First, the weights, which is a matrix of shape Cout by Cin, so 4 by 2 for us. Second, the biases, which is a vector of shape C out, so just 4. To make this super clear, let's manually set the weights and biases to some nice simple numbers. For the weights, we'll set the data to a torch tensor. The first row is 1, 0. The second is -1, 0. The third is 0, 2. And the fourth is 0, -2. For the biases, we'll just use 1, 1, -1, and -1. Finally, our input vector will be 0.5 and -0.5. Okay, let's manually calculate just the first output element together. Output at index 0 equals input at 0 times weight at 0, 0, plus input at 1 times weight at 0.1 plus the bias at 0. Plugging in the numbers, that's 0.5 times 1.0 plus minus 0.5 times 0.0 plus 1.0, which simplifies to 0.5 plus 0 plus 1.0, which equals 1.5. Now let's see what PyTorch gives us. We call output vector equals linear layer of our input vector, and we print them both out. The input is 0.5 minus 0.5, and the output is 1.5, 0.5, -2.0, and 0.0. It matches perfectly. That's it. See? No magic at all. Okay, now let's trace a single token's journey through the entire MLP. Our input will be a single token vector with C equals 2. The MLP will expand it to 4 times C, which is 8. So our input X is a tensor of shape 1, 1, 2 with the values 0.5 and -0.5. Step 1, the expansion layer, FC. This is an NN.linear layer going from 2 dimensions to 8. We'll set a manual seed for reproducibility and create some random weights and biases. Then we calculate x expanded equals fc of x, and after the expansion layer, the shape is now torch.size of 118, and the values are something like 0.52, minus 1.02, -0.32, and so on. Our vector has successfully been expanded. Step 2, the GELU activation. GELU is just a smooth alternative to RELU that squashes negative values towards 0. If you look at the table, an input of 2.0 becomes about 1.95, but an input of -1.0 gets squashed down to about -0.04. So let's apply it. X underscore activated equals f.gelu of X underscore expanded. After GELU, the shape is still 118, but look at the values. The positive numbers are mostly the same, but the negative ones, like -1.02, have been squashed down to -0.04. This is that critical nonlinear step. Step 3, the contraction layer, proj. Now we just project that 8-dimensional vector back down to our original 2 dimensions. Proj equals nn.linear from 8 to 2. We set another seed, create some random data for it, and then x projected equals proj of x activated. After the contraction layer, the shape is back to torch.size 112. And the values are now 0.33 and -0.15. And finally, step 4, dropout. The last step is to apply the dropout layer. During training, this layer randomly sets some elements to 0 for regularization. But during inference, when we're actually generating text, the dropout layer does absolutely nothing. It just passes the data through. So, the final result. Our input was a vector with 0.5 and -0.5. It went through the MLP's thinking process, and the output is a new vector with 0.33 and -0.15. The key takeaway here is that the MLP transforms the input vector while preserving its shape. It goes from B, T, C, and it ends up as B, And this is super critical because it allows us to add this output back to the original input using something called a residual connection, which we'll explore next. So, let's recap. We have now built both major components of our transformer block. We have causal self-attention for communication and the MLP for thinking. Now, we need to assemble them. We need to put them together into a robust, repeatable block. But we can't just stack them one after another. To make deep learning actually work, we need a special ingredient. We need the residual connection. Our entire focus in this section is on the humble plus sign. Let's look at our gpt2_min.py file inside the block class. The class has an init method with layer norm, attention, another layer norm, and an MLP. But the magic is in the forward method. Look at this line right here. This is our focus, the addition operation. X equals x plus self.addAttend, open parenthesis, self.ln1, open parenthesis, x, close parenthesis, close parenthesis. And look, it happens again right after. X equals x plus self.mlp, open parenthesis, self.ln2, close parenthesis, open parenthesis, x, close parenthesis. This simple pattern, x equals x plus something, is one of the most important breakthroughs in the entire history of deep learning. So why? Why can't we just do this? X goes to attention, then to the MLP, then to the next block. Why do we need that extra plus X? Well, when you build a very deep network, you run into a huge problem called the vanishing gradient. It's like a long game of telephone. You know how that works, right? The learning signal has to travel backward, all the way from the final output through every single layer back to the very first one. With each step backward through a layer, the signal gets a little distorted, or weaker, and weaker, until it has vanished. The early layers of the network learn absolutely nothing. The residual connection provides a brilliant solution by creating a shortcut, or an express lane. Look at this diagram. Your input X comes in at the top left. It flows into a sublayer which contains layer norm and causal self-attention. That sublayer does its computation, and its output goes to this plus sign. But here's the magic. Look at this other arrow. The original input X also flows directly to that plus sign, completely bypassing the sublayer. That's the residual connection, the express lane. During backpropagation, the gradient can flow directly through this addition operator. It completely bypasses all the transformations inside the attention layer. It's an uninterrupted highway for the gradient to travel back in time. This fundamentally changes what the network is trying to learn. Without residuals, you're telling the network, here is a blank canvas, paint a masterpiece. Good luck with that. With residuals, it's easy. You're saying, here is the current painting, which is X. Now, just make these small adjustments, which is the output of self.lbl. It is so much easier for a network to learn how to make small iterative adjustments than it is to learn the entire transformation from scratch at every single layer. Let's do a walkthrough with numbers to see just how simple this is. The operation is just a simple element-wise addition. We'll start with an initial input vector for a single token. We'll call it xInitial. Let's say it's a tensor with the values 0.2, 0.1, 0.3, and 0.4. Now, that input goes through the attention sublayer, and it produces an output. We'll call it attention output. This is the adjustment to be made. Let's say its values are 0.1, negative 0.1, 0.2, and negative 0.3. Now for the residual connection. X equals X plus, let's look at the result. The original input x was 0.2, 0.1, 0.3, 0.4. The adjustment from attention was 0.1, minus 0.1, 0.2, negative 0.3. So, the new value is just the sum. The value after the first residual connection is a tensor with 0.3, 0.0, 0.5, and 0.1. It's that simple. It's just addition. Critically, the shape of the tensor remains unchanged. Look at this table. In step 1, the self.attention operation takes an input of shape BTC and produces an output of shape BTC. Its whole purpose is just to calculate the update, or the residual. Then, in step 2, the x plus operation takes that same shape, BTC, and outputs, you guessed it, BTC. Its only job is to apply the update to the original. We have now added the first piece of glue to our block. This express lane is what allows us to build much deeper and much more powerful models. But a highway with no rules can lead to chaos. Let's dive back into our code. Let's look at our block class again. Our focus this time is on these two lines, self.ln_1 and self.ln_2, and more importantly, where they are applied. Inside the init method, you can see we define them right here. We have self.ln_1 equals in.layernorm, and self.ln_2, another in.layernorm. Now here's the key part. Look at the forward method. We apply layernorm before the data goes into the sublayer. See? It's x plus self.tts of self.ln_1 of x. And then we do it again before the MLP layer. It's x plus self.mlp of self.ln_2 of x. So what on earth is this doing? Well, it's solving a really big problem. The problem of trying to hit a moving target. As data flows through the network, the distribution at each layer is constantly changing during training. The mean, the standard deviation, it's all over the place. This is called internal covariate shift. Think of it like this. Each layer in our network is trying to learn, but the target it's aiming for is constantly moving. It makes it incredibly difficult for the network to learn anything efficiently. It's like trying to shoot arrows at a target strapped to a bucking bronco. Good luck with that. Layer normalization is the technique that tames the bronco. It acts as a stabilizer. For each individual token's vector, this is really important, it performs these steps. First, it calculates the mean, which we'll call mu, and the variance, sigma squared, across that single vector's embedding dimension. That's the C dimension. Second, it normalizes that vector to have a mean of 0 and a standard deviation of 1. Look at this formula. The new vector, x hat, equals x minus mu, divided by the square root of sigma squared plus a tiny little epsilon to prevent dividing by 0. And third, it applies learnable parameters, gamma and beta, to scale and shift the distribution back. The final output, y, is gamma times x hat plus beta. This gives the model back control after we've stabilized everything. Okay, that was a lot of theory. Let's walk through this with numbers. This is how it will click. We're going to trace the process for a single token's vector. And we'll say its embedding dimension C is equal to 4. Step 1, the input vector. Let's say we have this tensor x token with the values 0.3, negative 0.2, 0.8, and 0.5. Right now, if we check, its mean is about 0.35, and its standard deviation is 0.41. It's a moving target. Okay, on to step 2, normalization. This is the x hat calculation. We take our input x token, we subtract the mean, and we divide by the standard deviation. And what do we get? Look at this. the normalized vector x hat is now negative 0.12, negative 1.33, 1.09, and 0.36. And its mean? 0. Its standard deviation? 1. Perfect. The target is no longer moving. Now for the final step. Step 3. Applying the learnable parameters gamma and beta. When we create a layer norm layer, like ln equals nn.layerNormC, PyTorch initializes two special parameters for us. The first is layerNorm.weight, which is our gamma. It starts as a tensor of all ones. The second is layerNorm.bias, our beta, which starts as a tensor of all zeros. So initially, multiplying by 1 and adding 0 doesn't change anything. But let's pretend the model has been training for a while, and it has learned that a different scaling is optimal for the next layer. Maybe it's learned that gamma should be 1.5, 1, 1, and 1, and beta should be 0.5, 0, 0, and 0. Now we apply this to our nice, stable, normalized vector. Y equals gamma times x hat plus beta. And here's what we see. Our final output vector is now 0.32, negative 1.33, 1.09, and 0.36. It's a stable, clean, and optimally scaled input for the next part of the network. Okay, one last crucial practical detail. Pre-norm versus post-norm. Look at this table. We have two main styles. On the left is pre-norm, which is what we use in our GPT-2 style model. Its equation is x plus the sublayer of layer norm of x. The normalization happens before the sublayer. On the right is post-norm, the original transformer style. Its equation is layer norm of x plus the sublayer of x. The normalization happens after. Now here's the important part, stability. Pre-norm is generally more stable. It makes it easier to train very deep networks without needing fancy learning rate schedules. Post-norm can be harder to train for very deep models and often requires a learning rate warm-up. In our code, you see x equals x plus self.att, self.ln1x. That is textbook pre-norm. So why does our code use pre-norm? Because it's more robust. By normalizing the input before it enters the attention or MLP layers, we keep the values in check and prevent the numbers from exploding. It just makes training smoother. So, with our residual connections providing the express lane and layer normalization acting as the stabilizer, this is the payoff. We have meticulously built every single component. The communication layer, the causal self-attention, the thinking layer, the MLP, the express lane, our residual connections, and the stabilizer layer normalization. Now we click them together. This is the code for the block class. This is the fundamental repeating Lego brick of the entire GPT-2 model. That's it. I'm serious, that's really it. And you already understand every single piece of it. Let's look at the blueprint of a block, the dunder init method. The constructor is just an assembly list. It's like the parts list for a Lego set. First, we have self.ln_1 equals nn.layerNorm. That's the stabilizer we just built. Then, self.attention equals causal self-attention. That's the communication layer you built. Then another stabilizer, self.ln_2. And finally, self.mlp equals MLP, the thinking layer. You built this too. There is zero new complexity here. It's just a container for the components we've already mastered. The forward method orchestrates the flow of data through these components, and it follows a simple, powerful mantra. Normalize, process, add. Let's trace the data's journey. Check out this flow diagram. The input X comes in, it flows into layer norm 1, then causal self-attention, and then it gets added back together with the original input. That output then flows into layer norm 2, then into the MLP, and gets added back again to produce the final output. Let's look at that first sublayer, the attention meeting. The code is x equals x plus self.enide of self.ln_1 of x. Let's break it down. First, we normalize. We apply self.ln_1 to x. The input is stabilized. Simple enough. Second, we process. That stabilized data enters the self.apro point, our communication layer. And third, we add. The result of all that is added back to the original x. That's the residual connection at work. Now for sublayer 2, the thinking time. The code is x equals x plus self.mlp of self.ln_2 of x. It's the exact same pattern. First, normalize. We stabilize the output from the first sublayer using self.ln_2. Second, process. Each token thinks about the new information inside the self.mlp. And third, add. The output is added back again. It's so elegant. The most critical property of this entire block is that the shape of the output tensor is identical to the shape of the input tensor. BTC. Always. This is what makes the block perfectly stackable. This stackability is the key to the transformer's power. A single block is like a single project meeting. It's a good first step, but complex problems require more. To build a deep understanding, we need a series of meetings, a symposium. For example, meeting 1, or block 0, figures out basic grammar and syntax. Then meeting 2, block 1, takes that and pieces together higher-level ideas. You fast forward all the way to meeting 12, block 11, and it achieves deep, nuanced, semantic understanding. This allows us to distinguish between width and depth. Look at this table. Let's walk through it. First, the concept of width, which comes from multi-head attention. What does it do? It's parallel processing within a layer. The analogy is a committee of 12 specialists in one meeting. Why? To analyze input from many perspectives at once. Now, let's look at depth, which comes from multi-layer models like this. What does it do? It's sequential processing across layers. The analogy here is a series of 12 meetings, each refining the last. And why do we do this? To build a hierarchical understanding, from simple patterns to abstract concepts. So how do we code this series of meetings? We use a special PyTorch container called nn.modulelist. In the main GPT-2 model's dunder init method, you'll see this line. Self.h equals nn.modulelist, containing a list comprehension. Block of config for underscore in range of config.n_layer. This simple line creates n_layer, say 12, separate instances of our block. This brings us to a crucial final question. Are the weights shared between these 12 blocks? Absolutely not. Each call to block of config creates 12 independent objects, each with its own unique weights. Why is this essential? Well, think about it. Layer 1 is processing raw embeddings. Layer 12 is making final refinements. Different layers need different skills. By giving each block its own set of weights, we allow each layer to specialize in its part of the job. We have now officially built our fundamental Lego brick, and we understand the strategy for stacking them. We have officially reached the summit. After building every single component from the ground up, we are now ready to assemble the final model. This section will feel like a victory lap. You are going to recognize every single line of code we look at. You built this. Let's look at the init method of our final GPT-2 class. This is the master blueprint, the one that organizes every single layer we've discussed. Here it is, class GPT-2, which inherits from nn.module. Inside the dunder init method, we take in our config object. We see 3 distinct parts. This constructor perfectly follows the high-level architecture we set out to build. Check out this diagram. We start with input token IDs, which flow into token and positional embeddings. Then, through dropout, into our N transformer blocks. After that, there's a final layer norm, then the language model head, and finally our output logits. It all fits together. Let's walk through this init method section by section and connect every line back to the section where you mastered it. First up, part 1, the input layers. This is the entry point of our model, converting raw token IDs into meaningful vectors. We have self.wte, our word vector dictionary that we built earlier. Then, self.wpe, the positional lookup table. You remember that from earlier too. And finally, self.drop, for regularization to prevent overfitting. Next, part 2, the core processing layers. This is the heart of the model, the deep part of deep learning. Here we have self.h. This single powerful line creates n_layer, say 12, independent instances of our block class. Data flows through these blocks sequentially, becoming more refined at each step, just like we discussed. And that brings us to part 3, the output layers. These are the final preparations before making a prediction. We have self.ln_f. This is a final layer normalization that provides one last stabilization step. It ensures the output vectors are well behaved before the final prediction. We mastered this concept earlier as well. We have now defined almost all the structural components of our model. We've built the entrance, the main processing tower, and the final stabilization stage. The only piece missing is the most important one for a language model, the layer that actually makes the prediction. How do we go from these complex, refined vectors back to a probability distribution over our entire vocabulary? We have reached the final architectural component of our GPT model. Our data has traveled a long journey. It started as embeddings, then went through that deep stack of transformer blocks, and was finally stabilized by a final layer norm. We now have highly context-aware vectors, one for each and every token in our sequence. The shape of our tensor is batch by sequence length, by embedding dimensions, or BTC. But here's the thing. This is just an internal representation. It's not a prediction. So how do we use these rich 768-dimensional vectors to predict the single next word? Let's examine the final piece of our GPT-2 model's init method. We've seen all the other parts, the token embeddings, the positional embeddings, the dropout, the transformer blocks, the final layer norm, and now this is the final architectural piece. Self.lmhead equals nn.linear, and then a very interesting line. Self.lmhead.weight equals self.wte.weight. We'll come back to that second line in a minute. So what is this LM head? It's actually just a simple NN.linear layer. Nothing fancy. Its job is to project from our internal vector space, that's the C dimensions, into the vocabulary space, which has vocab size dimensions. But here is the brilliant twist. This projection, this simple linear layer, is applied independently and in parallel to every single token's vector along the T dimension. So instead of making one prediction, it makes T predictions. Let's look at this table to see what's happening. Our input to this layer is the tensor we've been working with a shape of BTC. The output from the LM head is a new tensor we call logits. Its shape is B by T by vocab size. And what does it mean? It contains a raw score, a logit, for every possible next token for each of the T input positions. This brings us to a crucial question. Why make T predictions? Isn't that just wasteful? This is one of the most brilliant design choices in the transformer. The answer depends on whether you are training the model or using it for generation. First, let's talk about efficient training. When we're training, we want the model to predict the next word at every single position in the sequence, all at once. For example, if our input is a crane ate fish, which has a T of 4, the model has to learn multiple things simultaneously. Given A, it has to learn to predict crane. Given A crane, it has to learn to predict ate. And given A crane ate, it has to learn to predict fish. Our logits tensor gives us all the predictions we need in a single forward pass. It's incredibly clever. Look here. Logits at index 0 in the T dimension is the prediction based on just A. We'll compare this to the target, which is crane. Then, logits at index 1 is the prediction based on A crane. We compare that to 8. And finally, logits at index 2 is the prediction based on A crane 8, which we compare to fish. And of course we know this works because our causal mask ensures the prediction at any position T only uses information from tokens 0 up to T. This parallel approach is incredibly efficient for training on a GPU. Okay, but what about number 2? For generation, or inference. When we want to generate new text, your intuition is correct. We are, seemingly, being wasteful. Imagine our input is a prompt, like a crane 8, where T equals 3. The model runs a forward pass and produces logits of shape 1 by 3 by vocab size. Now, here's the key part. We throw away the predictions from the first 2 positions. We only use the prediction from the final position, logits sliced at -1, to sample the next word. This might seem inefficient, but it's a trade-off. The architecture is heavily optimized for the massively parallel computations needed for training. We just leverage that same powerful architecture for inference, even if we only need the result from the final time step. It's a pragmatic and very effective choice. And now, for the grand finale. Let's look very closely at the last 2 lines of our model's dunder init method again. Self.lm head equals inin.linear. And then self.lm head.weight equals self.wte.weight. The second line is a simple but profound optimization known as weight tying. It's not just copying the weights. It is telling PyTorch that the weight matrix for the LM head is the exact same object in memory as the weight matrix for our token embedding layer, WTE. They share the exact same weight matrix. This means when backpropagation updates one, it simultaneously updates the other. They are tied together. So, why does this make perfect sense? Let's analyze the roles and shapes of these 2 weight matrices. Check out this table. First, our WTE layer. Its weight attribute, self.wte.weight, has a shape of vocab size by n embed. Its role is to convert a token ID, which is a row index, into a meaning vector. It's an ID to meaning map. Now look at the LM head. Its weight, self.lmhead.weight, also has a shape of vocab size by n embed, and its role? To convert a meaning vector into a score for each token ID. It's a meaning to ID map. They have the exact same shape, and their functions are perfectly symmetric. One goes from ID to meaning, the other goes from meaning back to ID. The core insight of weight tying is that these two operations should be inverses of each other. The vector that represents the meaning of the word cat should be the same whether cat is an input or an output. It's just logical. And the benefits are huge. First, massive parameter reduction. For GPT-2 small, this weight matrix has 50,257 rows times 768 columns. That's roughly 38.5 million parameters. By tying the weights, we eliminate the need to store and train a second, separate matrix of this enormous size. We just saved almost 40 million parameters with one line of code. It's absolutely brilliant. Second, you get improved performance. This acts as a powerful form of regularization. By enforcing a sensible, logical architectural constraint, it can prevent overfitting and lead to better, more stable models. We've built the entire GPT model architecture, from the embeddings all the way to the final language model head. We have a fully assembled machine. But right now, it's an engine full of millions of randomly initialized weights. It can't write a single coherent word. So, how do we teach it? How does it learn? This section is all about that process. It's about the journey of data through our model to produce a single, crucial number: the loss. This loss value quantifies exactly how wrong the model's predictions are, and it's the signal we use to update every single weight in the entire network. Let's focus on the forward method. You've seen the first half of this journey. Now we're going to complete it. Here's the code from our GPT-2 class. We've already built the init method. Now we're in the forward method, which takes self, IDX, and an optional targets argument. We know all the first parts: the embeddings, the dropout, the blocks, the layer norm, the LM head. This all produces our logits tensor. Okay, this is our focus now. You can see we initialize loss to none. Then, if targets is not none, we calculate the loss. And it's all in this one line. Loss equals f.cross_entropy of logits.view-1, logs.size-1, comma targets.view-1. How does this one line teach the entire model? Let's find out. The goal of training is beautifully simple. It's called next token prediction. Given a sequence of words, the model's entire job is to predict the very next word. So for each chunk of our training data, the input, IDX, is the sequence, and the targets are that same sequence, just shifted one position to the left. Look at this example. If the input IDX is A, crane 8, the targets are crane 8, fish. The model has to learn to make these predictions at every single step in the sequence. Let's do a quick walkthrough of the forward method up to this point. First, we get our embeddings. We create token and positional embeddings to get our initial BTC tensor. We've covered this. X equals self.wte of IDX plus self.wpe of pos. Second, we process it through the blocks. The tensor flows through the stack of transformer blocks, becoming more and more context aware. For block in self.hx equals block of x. Third, we get the logits. The final vectors are projected into our logits tensor, which has a shape of bt vocab underscore size. Okay, now for the main event. Calculating the loss, one number to rule them all. We now have our logits, which are the predictions, and our targets, the correct answers. The final step is to compare them. Here's that line again. Loss equals f.cross underscore entropy, and then we have those dot view calls inside. So what's with the dot view? f.cross underscore entropy expects 2D inputs. The dot view function is simply PyTorch's way of squashing dimensions together to get the right shape. Let's make this crystal clear. Look at this table. Our logits variable starts with a shape of bt vocab underscore size. When we call dot view on it, we reshape it to b times t, comma, vocab underscore size. The purpose of this is to create a 2D tensor where each row is a prediction for one specific token position. Now for targets. It starts with shape bt. When we call dot view -1, it becomes a 1D list of shape b times t. Its purpose is to be a simple 1D list of the correct answers, perfectly aligned with the predictions we just made. Now for the most important part of this entire section. How does cross-entropy actually calculate the loss? The crucial point is that it calculates the loss for each of the b times t predictions individually, and then it averages them to produce a single final scalar loss value. It does not add them up. It takes the mean. This is so important because it keeps the loss on a consistent scale. Whether your batch size is 8 or 8,000, it makes training stable. Let's put it all together. The full training loop, a story in 6 stages. We're going to tell the complete story from a raw stream of text all the way to a weight update. Let's say our block size, or T, is 4. Step 1. The raw data stream. Imagine our training data is just one long river of token IDs, something like 5, 12, 8, 21, 6, 33, 9, 4, 15, 7, 2, and so on. Step 2. Creating input target pairs. From that stream, we just grab chunks. For example, sample 1 might have an IDX of 5, 12, 8, 21, and its targets would be 12, 8, 21, 6. Sample 2 would pick up where that one left off. Its IDX would be 6, 33, 9, 4, and its targets would be 33, 9, 4, 15. Now, the batch. This is our unit of work. We stack these samples to form a batch, let's say with a batch size of b equals 2. This lets us process data in parallel on a GPU, so our input IDX has a shape of 2 by 4. You can see the two samples stacked on top of each other. And our target tensor also has a shape of 2 by 4, with the corresponding targets for each sample. Okay, let's walk through this entire 6-stage process together, step by step. This is how the learning actually happens. First, stage 1, the forward pass. The batch, our IDX tensor, is fed into the model. The model processes both samples and outputs a logits tensor of shape 2 by 4 by vocab size. Easy enough. Next, stage 2, loss reshaping. We prepare the logits and targets for the loss function. Logits gets reshaped to 8 by vocab size, and targets gets reshaped to a flat list of 8 numbers: 12, 8, 21, 6, 33, 9, 4, 15. Stage 3, cross-entropy calculation. The function calculates the loss for each of the 8 individual pairs. Let's imagine the results. For the first prediction, maybe the loss is 2.5. For the second, 3.1. then 1.9, 4.2, and so on. We get 8 separate loss numbers. Now, stage 4, the most important one, averaging. We average these 8 individual losses. So we do 2.5 plus 3.1 and so on divided by 8. And let's say our final loss is 3.0. That is our single scalar loss value. Stage 5, backpropagation. We call loss.backward on that single scalar value, 3.0. PyTorch then calculates the gradients for every single weight in the model based on that average loss. And finally, stage 6, the weight update. The optimizer takes one step. Optimizer.step updates all the model weights, nudging them in a direction that would have made that average loss of 3.0 a little bit lower. This entire 6-stage process is one training step. For each batch, there is only one backward pass and one weight update, and it's all driven by the average performance across all the token predictions in that batch. We have now closed the loop. We've gone from a raw stream of text to a trained model.
We have built the entire GPT architecture. We have understood how it's trained. Now it's time for the payoff. It's time to unlock its true purpose, generating new, coherent text from scratch. The process is called Autoregressive Generation, which sounds complex, but it's based on a beautifully simple loop that you can probably guess right now. The core idea, the generation loop. Let's break it down. 1. Predict. Feed the current sequence in, get a guess for the next word. 2. Sample. Roll the dice on that guess and pick one new word. 3. Append. Add the new word to the end of the sequence. And 4. Repeat. Go back to step 1 with the new, longer sequence. That's it. That's the entire algorithm. Let's do an example walkthrough. We give our trained model the starting prompt, a crane. So, iteration 1. The initial IDX is 512. First, predict. We feed 512 into the model. It gives us scores for the next word. Next, sampler. Let's say it gives 8 a 40% probability and lifted 35%. We roll the dice and get 8, which has an ID of 8. Finally, append. Our new sequence is now 512.8. Okay, on to iteration 2. Our current sequence is a crane 8. The current IDX is 512.8. So first, we predict. We feed this new, longer sequence, 512.8, into the model. Now we sample. Having seen 8, the model gives a massive 90% probability to fish. We sample and get fish, which has an ID of 21. And finally, we append. Our sequence becomes 512.821. This loop continues, one word at a time. Now let's connect this simple loop to the real code from gpt2_min.py. Here's the code on screen. We're looking at the generate method inside the GPT-2 class. Now, don't worry, we're going to break this whole thing down piece by piece. First, let's look at number 1, at torch.noGrad. This is a crucial optimization. It tells PyTorch not to calculate gradients, saving massive amounts of memory and computation. Remember, we're not learning, we're just predicting. Number 2, context cropping. The model has a fixed context window, the block size. If our generated sequence gets too long, we must crop it to only feed in the most recent tokens. This is the model's short-term memory. Number 3, predict. Look at this line. Logits equals logits, :-1, : This is the key step. We throw away all predictions except for the very last one. This single line connects that wasteful training process to efficient generation. Number 4, sample. f.softmax converts our final scores into probabilities, and torch.multinomial performs the dice roll, picking one token based on those probabilities. And finally, number 5, append. The newly sampled next token is concatenated to the end of our IDX sequence, preparing it for the next iteration of the loop. Controlling the magic, the creative knobs. This is where you become the artist. Let's look at this table. We've got two main parameters. First, temperature. This rescales the logits before softmax. A low temperature, anything less than 1.0, makes high probability words even more likely. The result is more predictable, conservative text. A high temperature, greater than 1.0, flattens the distribution, making rare words more likely. The result is more random, surprising, and creative text. Next, we have top K. This truncates the distribution. It considers only the K most likely tokens. So if top K equals 50, it throws away all but the 50 most likely words and samples from that smaller set. The result? This prevents very rare or nonsensical words from being chosen, making the output much more coherent. Conclusion: the transformer has clicked. We have reached the end of our 90-minute journey. We started with this file, gpt2_min.py, that seemed like a dense, magical black box. We made a promise to take that box apart, piece by piece, until the magic dissolved into understandable, elegant engineering. And that is exactly what we did. We started with token and positional embeddings. We built the intuition for self-attention and its causal mask. We scaled it with multi-head attention. We added the thinking MLP and glued it all together with residual connections and layer normalization to form a block. Finally, we stacked the blocks, added the language model head, and understood training and generation. The gpt2_min.py file is no longer a mystery. Every @torch.nograd, every .view, every plus sign now has a purpose and a story. The transformer has clicked.